Welcome to today's deep dive. For most of us, heating a house usually just feels like turning a little thermostat dial on the wall and forgetting about it.
Yeah, it's a completely invisible process until the bill arrives, right?
Exactly. But today we're looking at a highly practical, fairly dense academic engineering text on autonomous heating systems. And our mission today is to decode it. We want to cut through all the shiny marketing hype you see at hardware stores and use raw math to figure out the absolute most efficient way to heat a building.
Like both in terms of energy and, actual financial cost.
Yeah. Okay, let's unpack this because this document takes that boring appliance in your basement and turns it into a high-stakes math puzzle.
It really does. And what's fascinating here is that the source material strips away all subjectivity. There's no guessing. It relies entirely on formulas, raw climate data, and thermodynamics to declare a clear winner in the heating game.
Which is exactly what we need. So to save money and energy, the very first thing we have to look at is the engine of the house, the boiler itself.
Right. That's where the math's...
So the text compares traditional gas boilers with something called condensing gas boilers. And it notes that traditional boilers operate at an efficiency of around 90 to 92%.
Which is pretty standard. You burn fuel... Some heat is lost, you get about 90% out of it.
Right, that makes total sense to me.
Yeah.
But then the source states that these condensing boilers boast an efficiency of 107.5 to 108%.
Yeah, that's where people usually do a double take.
Right. I mean, it gives a concrete example for a 200 square meter house with a 20 kilowatt heating load. A traditional 24 kilowatt boiler uses about 3.03 cubic meters of gas per hour at max capacity.
Yeah.
But a 22 kilowatt condensing boiler only needs 2.38 cubic meters per hour to do the exact same job.
It's a massive difference.
But wait a second, 108% efficiency? That literally breaks the laws of thermodynamics? Like, how can a machine output more energy than you put into it?
Well, the short answer is it doesn't. You're not actually breaking any physical laws.
Okay, good to know.
Yeah. It's about the math they use. The text bases its formulas on something called the lower heat of combustion. For natural gas, that baseline value is 33.5 megajoules per cubic meter.
Okay.
But that specific baseline metric assumes that a whole lot of energy is just naturally going to be wasted. Because when you burn gas, you produce water vapor, right? Steam.
Right, and steam is incredibly hot.
Exactly. It holds a ton of energy, which physicists call latent heat. Traditional boilers just vent that steam outside, so that baseline calculation assumes you're throwing that heat away.
Oh, I see.
But these new boilers operate in a condensing mode. They capture that exhaust, cool it down so the steam condenses back into liquid water, and then they harvest all that trapped latent heat and push it back into your house.
Wow.
So relative to that artificially lowered baseline metric, the effective efficiency pushes past 100%. The math simply works out to a massive reduction in fuel consumption.
Which sounds amazing. I mean, understanding the hourly gas savings is great in theory, but the text also points out that condensing boilers are significantly more expensive to buy.
Oh, absolutely. The upfront cost is much higher.
So the big question for you as a homeowner is, does the math actually justify that upfront cost? To answer that, we're diving into a specific case study from the text, calculating the payback period for a house in the city of Rivne, Ukraine.
Yeah, and they use real climate realities for this. Rivne has a 182-day heating season.
That's basically 6 months, roughly 400 and 320 hours.
Right. But obviously you aren't running your boiler at maximum power 247 for 6 months straight.
You'd cook yourself alive.
Exactly. So based on Rivne's climate data, the average winter temperature is just barely above freezing, about 0.1 degrees Celsius.
Okay.
But the system has to be built to survive the coldest 5 days, which hit minus 21 degrees Celsius. To maintain a nice 20-degree indoor temp across all those fluctuations, the text calculates what's called a load factor.
Right, and for Rivne, that load factor is 0.485, meaning the boiler averages out to running at about 48.5% capacity over the season.
Precisely. So let's look at the financials with that load factor in mind. The upfront cost of the traditional boiler is 18,148 Ukrainian hryvnia,
Okay.
while the condensing boiler is 34,554 hryvnia.
Wow, that is almost double the price.
It is a huge jump. However, when you factor in that 0.485 load factor over the 182 days, the condensing boiler saves you 1,378 cubic meters of gas annually.
Every single year.
Exactly. And at a price of 7.99 hryvnia per cubic meter, that is a direct saving of 11,010 hryvnia every year.
So what does this all mean? It's kind of like buying a hybrid or an electric car, right? The sticker shock at the dealership really hurts, but the pain completely vanishes when you see how much you save by bypassing the gas pump every week.
That's a perfect analogy. And if we connect this to the bigger picture, the formula for the payback period, which is just the difference in initial cost divided by the annual savings, it reveals that the expensive condensing boiler pays for its premium in just about 1.5 years.
Just 18 months.
Yep. In engineering, upfront cost is often just a distraction. Long-term operational efficiency is really the only metric that truly matters.
That's wild. Okay, so we've established that the condensing gas boiler is a clear financial winner against traditional gas. But what if you want to step away from natural gas entirely?
That's a very real scenario for a lot of people.
Yeah, maybe you're off the grid. Well, the text provides this massive, mathematically calculated cage match of alternative fuels. We're going to run through the annual costs of heating that exact same 200 square meter house with different energy sources.
And the numbers are all over the map. Let's start with liquid fuels, like diesel or furnace oil.
Okay.
The house burns roughly 2 liters an hour. And because petroleum is so expensive, it costs roughly 237,600 hryvnia a season, assuming 55 hryvnia a liter.
That is astonishingly expensive. What about liquefied gas, like propane butane?
Better, but still pricey. That costs about 86,400 hryvnia a season.
Okay, so a lot of people are pushing for electric heating now. What does the text say about that?
Well, electricity's tricky. The text actually notes that an electrode boiler is way more efficient than a standard 10 boiler. It consumes about 4,167 kilowatt hours a month compared to 7,000.
That's a big drop in consumption.
It is, but even at 2.64 hryvnia per kilowatt hour, it still costs about 66,000 hryvnia a season.
Got it. So let's look at solid fuels. Firewood, the absolute classic, costs roughly 77,760 hryvnia. Coal is definitely cheaper at 40,608 hryvnia. But then we get to pellets.
Right, compressed biomass pellets.
Here's where it gets really interesting.
Yeah.
To generate the required 43,200 kilowatt hours for the whole season, you could use wood pellets, which yield 4.7 kilowatt hours per kilogram, or straw pellets at 4.
Yep.
But the text brings up sunflower husk pellets, and wood is obviously the classic heating fuel, right? But the text claims sunflower husks have an energy density of 5 kilowatt hours per kilogram, literally beating wood.
It's hard to believe, honestly.
It is. Imagine heating your home with agricultural sunflower waste. Like, why is this specific detail even included here?
Well, this raises an important question about our assumptions regarding energy. We tend to think of heavy, solid wood as the ultimate fuel.
Right.
But the text points out that while wood pellets are considered higher quality, mostly because they produce a lot less ash and are cleaner to handle, the raw thermal math proves that sunflower husks actually release the most heat.
Because they're basically soaked in residual oils, right?
Exactly. They are incredibly energy dense, and using them brings the seasonal cost down to just 33,540 hryvnia.
Wow, so it's the absolute cheapest option.
It is. But furthermore, the text warns that these massive cost numbers for diesel, propane, and pellets, they don't even include the cost of physical delivery.
Oh, true. You have to get thousands of kilograms of pellets delivered.
Right, and you need a place to store them. When you factor in the logistics of moving all that physical material, natural gas starts to look even more attractive.
Because it just quietly flows right through a pipe into your house.
Precisely.
Okay, so let's say you've chosen this hyper-efficient condensing boiler and you've picked your optimal fuel. You might think the job is completely done.
Not quite.
No, because the text shifts to the final critical engineering hurdle. You have to safely get the exhaust out of the building.
Yes, the chimney. Or the flue system.
Right. And designing the chimney is not just a matter of putting a metal pipe on the roof and calling it a day.
No, it requires incredibly strict mathematical calculations based on thermodynamics and fluid dynamics.
Which blew my mind. The text explains that the chimney diameter relies on something called the effective height.
Right. The effective height is the vertical distance between where the exhaust enters the pipe from the boiler and where it finally exits out into the air.
So if the exhaust enters the chimney at 1.5 meters off the ground and exits the roof at 12.5 meters, your effective height is 11 meters.
Exactly. You're just measuring that column of rising air. And for a standard 20 kilowatt boiler at an altitude of 150 meters above sea level, an 11-meter effective height requires a chimney diameter of exactly 12 centimeters.
Wait, the altitude of the building matters.
Oh, absolutely. Altitude changes air pressure, which changes how the smoke naturally drafts or rises up the pipe.
That is so specific. But then the text gets even more complex. It looks at apartment buildings with individual heating units in every apartment.
This is where the math is literally a matter of life and death.
Yeah, because you have to calculate the total flue gas mass flow in grams per second, which is a wild way to measure smoke.
It really is.
The text gives an example. Say a building has two 18-kilowatt boilers, which produce 13 grams per second each. Then three 8-kilowatt boilers doing 7 grams per second each, plus two big 24-kilowatt boilers.
You have to sum all of that up.
Right, so let's say it totals 81 grams per second of exhaust gas trying to escape all at once. Suddenly, the required collective pipe size jumps all the way to 25 centimeter.
You need a much bigger pipe to handle that mass.
It's just like urban traffic design. You can't force 81 grams per second of exhaust traffic down a one-lane, 12-centimeter country road. You have to build the 25-centimeter superhighway to prevent a literal disaster.
That's a brilliant way to put it. And it synthesizes perfectly what the text is trying to tell us. Efficiency and safety are deeply intertwined.
Yeah.
The most advanced, money-saving, 108% efficient condensing boiler will completely fail, or worse, become dangerous, if the exhaust system isn't precisely matched to its exact aerodynamic flow and the geographic altitude of the building.
The whole system has to be in perfect mathematical harmony.
Absolutely.
So, as we wrap up our journey today, it's wild how a dry engineering document reveals this high-stakes world hidden right inside our walls.
It really does.
A world where 108% efficiency is actually real, where agricultural sunflower husks mathematically beat premium firewood, and where chimney pipes are basically just scientifically scaled superhighways for toxic gas.
It really makes you appreciate the engineering all around us. And I'd leave you with something to mull over. This text proves that the true cost of a system is almost entirely in its daily operation, not its initial purchase. So whether it's the heating system in your home, the car you drive, or even the appliances in your kitchen, what other invisible systems in your daily life have hidden efficiencies and operational costs just waiting to be calculated?
That is a great question to end on. Thanks so much for joining us on this deep dive, and we'll see you next time.